Hey guys, welcome to the 5.3 notes part 1. This has to do with the quantum mechanical model of the atom. So the first thing to talk about is when you have a specific or quantized amount of energy. So a quantized amount of energy is just a specific amount. You can't have variations. It's a specific packet. When it's exposed to an atom, the electron jumps from its ground state. So right here is ground state, which is what we went over for the electron configuration. So wherever we think electrons are going to be based on their normal principal ideas, so the Aufbau rule, Hund's, and Pauli's exclusion principle, all those rules, those are to determine the ground state of an atom, of the electrons in an atom. So check out what happens. If you've got some energy and it hits an atom, that energy gets absorbed by the electrons and they jump to, it's called the excited state. So it was in the ground state and then some energy hit it and it goes whee and it goes up to a higher energy level. And then it's like going around at a higher energy level. So imagine you have a toddler and the toddler is the electron, and then you give the toddler some candy, a lot of candy. What does the toddler do? It starts running around the room. The toddler's running around. Well, eventually, after running around for a while, that excited electron, or excited toddler, is going to return to a lower energy level, or the ground state. And when it does that, see, here's the toddler, or the electron, in the high energy, like, woo, moving around the atom. And then as it goes down, the energy it had absorbed, it's going to release. And it's going to release, it's called photons. So photons are these packets of energy, and they're in the form of electromagnetic radiation. And that's the whole principle of what we're going to talk about today is electromagnetic radiation. What you need to know is all photons travel at the speed of light. And the speed of light is 3 × 10⁸ meters per second. Okay, how much is that? Well, that's 300 million meters in 1 second. Like 1 Mississippi. Boom. Okay. Let's make that a little more relatable. 300 million meters, so that's 300,000 kilometers. We're in America, we don't use that. So that's 187,500 miles. Light travels that far, 187,500 miles in just 1 second. Well, how big is that? That's really far for the human scale. I mean, the circumference of the Earth is only 25,000 miles. So that's saying light can circle the Earth, if it did that pattern, like 7 times in a second. So it's really moving really fast. Let's look at how they travel. So photons travel in these wave patterns. So the photon you can think of as a particle that's moving in this pattern. So it starts here, goes up, down, down. The first thing you need to know is the wavelength. That's the distance between 2 equal points on a wave. So from here to here. So the length from the top of a wave to the next top of the wave. So literally wavelength. It's denoted in this Greek symbol lambda. And it's in the units of meters because it's a length. The other thing we want to talk about is frequency, which is this Greek symbol nu. It looks kind of like a curvy V. And it's the number of times along a point of the wave that it hits the crest. So right here. So and it's in the unit of hertz. Like, it sounds like it hurts you, like you got punched, but H-E-R-T-Z, H-Z, and that's per second. So how many times does this happen per second? So if this were a wave, and this was where that particle traveled in 1 second, which isn't it, because we know that in 1 second this is traveling 187,500 miles. This is not that long, but we're going to pretend for a second it is. What's the frequency of this? If this is 1 second, will it be 1, 2, 3, 4, because it's saying it did all that in 1 second, so 4 hits per second. And like I said in the last slide, all electromagnetic waves travel at the speed of light when they're in a vacuum. Let's compare these two waves. So I've got a wave up here and a wave down here. First, let's talk about the wavelength. So what's the difference wavelength here distance from crest to crest versus the wavelength here, distance from crest to crest. The top one has a larger wavelength, the bottom one has a smaller wavelength. What does that do to the rest of it? Well, let's talk about frequency. How many hits per second? So this has 1, 2, 3, 4 times it hits the top in our frame. This one has 1, 2, 3, 4, 5, 6, a lot more. So when you have a larger wavelength, you have a lower frequency, less amount of times it reaches the top. If it takes more distance, then you're not going to hit the top as much. Versus on the bottom, if you have a smaller wavelength, then it's going to come to the top more often, so it has a higher frequency. What about in terms of energy? Well, just in general, how does it look? Which looks like it takes more energy, going like that or going like that? The first one is lower energy. This guy has lower energy. It doesn't take as much energy to follow this pattern as it does to go like that. Even like me just following it with the mouse, that took more work for me to do here. So this has a higher energy. Here are your types of electromagnetic radiation. So you have radio waves, microwaves, infrared, visible light, ultraviolet, X-ray, gamma rays. And you've probably heard of some of these, like your radio waves is what carries the AM, FM. It also works with like your cell phone. Microwaves is what heats your food. Infrared is heat. Visible light is what we see. So when you see like a rainbow in the sky, you're seeing all the different types, all the different colors that are in the sunlight that hits the earth. Ultraviolet is also part of sunlight. You notice it's like right over here after violet in the colors, so it's like just beyond violet. Ultraviolet, that's what damages your cells and causes cancer. X-rays, you might have had an X-ray if you've ever had a broken bone or thought you had a broken bone. And then gamma rays are really, really, really high energy. One of the things I like about this slide is it really shows the size of the wavelengths. So like a radio wave, how big are those wavelengths? Well, in a radio wave, it's actually about the size of a football field between each crest in that pattern. For example, infrared, that's going to be about the size of a bacteria to go in between each, which we know bacteria are super small, we can't even see them. But then gamma rays, it's so small that the size between these wavelengths, like this is really not done to scale at all, is the size of like a nucleus of an atom. Crazy small. If you notice in here, visible light, they've broken it down into the rest of it. Out of every type of EM radiation, we only see a little bit. Other organisms can see other things, like a mosquito can actually see an infrared. That's how a mosquito knows exactly where to bite you, because it can see the heat coming off of your blood vessels, and that's where it knows that's where its food is. But we only see this little bit, and we believe it's because of evolution. It has to do with which wavelengths could get through the water, because we believe that humans evolved initially in water, and then there was no need to adapt. It gets us everything we need, so it's we don't see that much of the spectrum, but we don't really need to see any more. So what is visible light? It's only a small portion of the EM spectrum, and it goes from red to violet. So if you look at this pattern, you've got red over here at 700 nanometers and violet over here at 400 nanometers. So this is obviously the longest, 700 nanometers wavelength. This is the shortest. So red has the longest wavelength, and thus we know it has the lowest frequency and the lowest energy. And the order it goes in, you've probably heard Roy G. Biv: red, orange, yellow, green, blue, indigo, violet. So that's the order of your visible light. This is the equation we're going to use for the rest of the lesson. It's the relationship between waves, and the speed of light. C is the speed of light, lambda is our wavelength, and if you want to think about like this kind of looks like a wave, I don't know the distance between, that's how I always thought about it. Frequency, like how many hits per second, so hit the top, hit the top. I don't know if that helps you at all, but that's how I see it. Let's talk about the units of this. So the speed of light, so speed is going to be in meters per second, like how many meters in 1 second, that's speed. Our lambda is meters, and our nu here, our frequency, is per second. So look at that. Meters per second on one side, meters per second on the other side. Works out. Let's do a problem. So calculate the frequency of radiation with a wavelength of 442 nanometers. Let's first say what we're given. So we're given the wavelength, which is lambda, and that equals 442 nanometers. Well, when we go back here with the units, do we want it in nanometers? No, we want it in meters. So we need to change out the nanometers for meters. Nano, nano, 10 to the negative 9. So just switch it, plug it in. When you have a prefix and you're trying to lose it, you can just replace it. Then let's write that nicely. You can type this into your calculator and I'll give it to you in scientific notation, 4.42 times 10 to the negative 7th meters. Now that we have our wavelength in the right units, we can plug it into our equation. So we're going to rewrite this, but with what we know. So we know c is the speed of light, so you can always write that as 3.0 times 10 to the 8th meters per second, equals lambda, so we're given lambda here, times nu, our frequency. And this is what you need to solve for. So this function is multiplication. To get rid of that, you need to divide. So if you're taking your frequency and multiplying it by 4.42 times 10 to the negative 7th meters, then you need to divide by that. Same thing, top and bottom of a fraction cancels out. If you did it to the right, you have to do it to the left. So it's over there. Is there anything that you see on the top and bottom that can cancel? If you said meters, you're right. You have meters on the top and meters on the bottom, so they're going to go. You're left with just that awkward per second. It sounds weird. You could also call it hertz. Hertz means per second. And then we're going to type this into our calculator. Just a refresher, to type this into your calculator, you would do 3.00, and instead of times 10 to the, always want to use E. So if you forgot or can't find that button, make sure to let me or whoever you're working with as your teacher know, and they can help you out with that. So 3.00 E8 divided by 4.42 E negative 7. Let's go ahead and type that in. You can freeze if you need more time. And did you get this? 6.79 times 10 to the 14th per seconds, or you can call that hertz. We have the next problem. It has to do with argon giving a laser output of EM radiation. And here is the frequency we're given. And we want to calculate the wavelength. And we want to calculate it in nanometers. So here's what we're given, the frequency. You can also put that like this, seconds to the negative 1. That means per second as well. Plug in what you know. You know c is the speed of light. You don't know lambda, that's the wavelength, that's what you're trying to find. And you know the frequency, that's what you're given. Divide both sides by the frequency. Cancel what cancels. Can you see what cancels over here? Take a guess. It was the per seconds. Okay? Plug it into your calculator. Go ahead and freeze the video to take time to plug it in. We'll see if you get what I get. Okay, here's what I got. Is that what you got? If not, talk to your teacher. So is that the final answer? Well, you tell me. Is that what it asked for in the problem? It asked for nanometers. So we need to do a little dimensional analysis. So I'm going to rewrite my answer, 4.89 times 10 to the negative 7th meters. And I do my little train tracks. Yep, they're back. I don't want meters, so I'm going to put that on the bottom. I need this, whatever's here, to be equal on top and bottom. Meters and meters are the same, but that won't cancel anything. I don't want meters, I want nanometers. So that needs to be on the top. But now these two things aren't equal, so I need my 10 on the bottom, nano, 10 to the negative 9th. Cancel what can cancel, and then plug it into your calculator. This is what you should get, 4.89 times 10 to the second nanometers. If you didn't get that, call a teacher over so that you can get some help. All right, same problem, but now it's saying, based on that, what type of electromagnetic radiation was that? So here was my answer, 4.89 times 10 to the second nanometers. That's the same thing as 489 nanometers. Where do you see that? Well, it's here in your visible light. See 400 to 700 nanometers? So we know it's visible light. Let's magnify that. So 489 is going to be somewhere in here. So it's going to be blue light. So that laser produced was a blue laser. All right, it's your turn. So here's a problem. You're given a wavelength, you want to find frequency. Don't forget micrometers. Micro is here, 10 to the negative 6th. I want you to freeze the screen, do the math on your own, and then when you come back, I'll give you the answer. All right, so did you get this? 2.28 times 10 to the 14th per seconds, or you could also say 2.28 times 10 to the 14th hertz. If you did, great. If not, call a teacher over. Next one. What's the wavelength of infrared radiation with a frequency of 4.44 times 10 to the 12th per second for hertz? You're looking for the wavelength, so freeze your video, solve it, and then come back. Did you get this? 6.75 times 10 to the negative 5th meters? If so, great, you're done. If not, call a teacher over and figure out what you did wrong. All right, happy chemistry. Here's a little joke for your way out.